You need no introduction. So go ahead, Katie.
Thank you. So yeah, I'm Katie, and I will be stretching the definition of dynamic walking today and talking about a wheelchair. So the main point of this wheelchair attachment that I'll be talking about is for populations of people that cannot be pushed from behind. So usually the caveat that people always say is, well, why don't you just have a motorized wheelchair? So you can think of at least two cases where you still want a caregiver involved in the transportation of the individual in the wheelchair. The first is actually the reason that this wheelchair was designed. Children with profound intellectual and mental disabilities who rely a lot, who have difficulty with verbal communication, and so having that body language is really helpful. And it's also useful for people with dementia. So I'll talk more about this later, but this design is being put onto a device that is going into different care homes so that people with dementia always have visual sight of their caregiver, so that if there are any memory losses, they do always know that that person is working with them. So obviously you can't just push a wheelchair from the side. Everyone understands physics enough to understand that. If you push from the side, it creates a moment which then turns the wheelchair and makes it difficult to push in a straight line. So obviously this creates a moment, and therefore the caregiver has to put in continuous effort to maintain that straight path. You can also see this in simulation. So if we ignore these different attachments and you just push the wheelchair forward from behind, it goes in a straight line. But if you push from a meter to the side, then you create that arced path. Therefore, we could add a passive solution to counteract that asymmetrical propulsion. This comes in the form of a simple caster wheel. This is nice because it's passive, therefore cheap. And there are some other non-electric systems, such as like different clutch designs, but that also kind of reduces your maneuverability. So in order to understand this caster wheel, we need a couple definitions. So the first is the swivel axis, which is the axis around which this caster wheel moves. For people who don't really know what caster wheels are, think of a cart, shopping cart that you push in a grocery store. The wheel spin axis is obviously what the wheel spins around. The cant angle is if you take that entire caster wheel unit and then you set it at an angle in the frontal plane. And then the bank angle is if you keep the swivel axis vertical and then you just angle the wheel. There is also the rake angle, so in the sagittal plane it's if you move the wheel forwards or backwards. So this design in particular, we mostly take advantage of that cant angle, so taking the wheel and then putting it at an angle. The movement around that swivel axis needs to be 0 if we want the movement forward to stay constant. So all of these simulations and experiments are done in steady state forward motion. So therefore, we're only going to look at the lateral force. So if your wheel is at an angle, the lateral force is in the direction perpendicular to the wheel's forward movement. So there were a lot of simulations and math that went into these conclusions, but I have 6 minutes. So I'm happy to talk offline, and it's also all contained within this master's student's thesis. But the two main theoretical conclusions that we come to are that the lateral force on the caster wheel can be simplified to the product of the cant angle, the normal force, and then a cosine relationship with the angle between the swivel axis and the cant. And then secondly, because this lateral force, in this picture the wheel is at an angle, but the lateral force actually ends up being perpendicular to the push force, and this means that when you have a properly designed canted wheel in the front, you need the same amount of force to push a person forward if you're pushing from behind without that wheel, or with the wheel pushing from the side. So we tested these two ideas in experiments. The first was just looking at the caster wheel on a treadmill. So we rotated the orientation of this wheel to test both the cant and also the rake. And we found that for the simulation results, which are this gorgeous cosine, our experimental results actually matched that relationship pretty well. And then to test the, sorry, you're gonna have to listen to the noise of the treadmill. And to test the pushing force hypothesis, we did the inverse of a push. We did a pull. So we pulled from the side with the handlebar and the caster wheel, and then we also pulled from the front. And we found that even though there is a slight change in the normal force, if you account for that, then there is actually no difference in pulling force. So in summary, the required pushing force does not increase, and that lateral force on the caster wheel is just a function of the normal force and your geometry. So this is all a product of Ziggy, which is a new startup that designs these wheels. And if you see Heike on this presentation and you're wondering why I'm not talking about the backpack, we can talk about that later. So thanks.
Perfectly timed. Yeah,
So you said that you're excited that it's passive because it's low cost, and so I assume low cost is one of the parameters. I was wondering how sensitive it is to that angle change, because that will affect manufacturing costs probably dramatically, right?
Yes. So it is. I have not done any tests on like any sensitivity analyses, but it is not so sensitive that any issues in like tightening the screws properly, any inconsistencies in our terrible treadmill, that doesn't seem to affect it. This device has been, I don't have any videos of this, but this device has been taken all over the Netherlands, and so just like over gravel roads and stuff like that, and it still seems to work pretty well.
Okay, awesome.
So, if someone had to go behind the wheelchair to push it for whatever reason, for example, limited space or navigating a step or something, does the caster wheel affect that? So it's harder to push it in a straight line from behind?
Yes, which is taken into account by the startup. They have a couple of additional design constraints that we didn't care to model because they're things like moving the caster wheel out of the way, so if you do have to push someone from behind. Also, collapsing that sidebar, if you imagine going through a doorway and that sidebar is sticking out. And then I think they may have added some other components as well. Yeah.
If you want to balance out the moments acting on the wheelchair, is it true that one particular angle of the caster wheel is used to balance out a particular pushing force? And then if that's the case, how do you, what happens if someone pushes a little harder, a little slower? Is there a way to make those kinds of adjustments, or how does that work?
So the pushing force, as a result of the simulation, if we go back to these two findings, the pushing force modulates your forward speed, but as long as you have the caster wheel is more a function of where you're pushing. So the moment arm.
So it doesn't matter how hard you push or not?
It just changes how fast you go. Yeah.
Doesn't this device make it harder to turn?
We also tested that in this case by doing these rotations in pure tangent, pure rate. It was difficult to test in this scenario because we had a small treadmill that was going forward at a fixed speed, but that is something that we want to consider. I think in the simulation we find that if you account for lots of assumptions and small angles, it does not necessarily make it that much harder. It's just like the vaguest statement I can make about this.
So the caster has that swivel degree of freedom, but a simple two-wheel cart with no swivel degree of freedom also goes straight. Why this selection and not that?
Because, so you're thinking of like a three-wheel cart. The wheel is going to go straight.
Yeah.
But that doesn't necessarily increase or add in a moment to counteract the moment that you get by pushing at a distance.
It does. It does. At least in theory. I mean, it'll scrub a little bit there.
But that depends on the geometry of where you put that wheel,
No,
correct?
I don't think so. But I think there might be plenty of reasons to do what you did instead, but I'm just sort of curious about the space and ideas there.
So this group has played with the placement of that third wheel and whether or not it is canted. That was not included in these dynamics. So these are all interesting questions, and I will post them to the group and let you know if I get internet and if they come up with any answers. Yeah.
Well, then, great discussion for later. Thank you so much.